We saw some systems of ODEs in the last video, but we didn't talk about one little wrinkle that makes things really interesting. What if your eigenvalues of your matrix turn out to be complex numbers? So we talked about those back in the last section, but we didn't really do any problems with them. So we need to actually be able to work with complex numbers in order to solve these systems, because those solutions actually turn out to be really relevant to a lot of problems. I'm not going to get into a lot of applications here, but just note that if you take a differential equations class, you will be talking about a lot of these kind of situations where these applications actually really require us to know what we can do with these complex eigenvalues. So remember, we're working with our system y equals a, or sorry, y prime equals ay, and we said that our solution was going to look something like, or at least part of our solution is going to be some linear combinations of e to the lambda t times some vector x. And what does it even mean to have the the eigenvalue lambda be complex? What would that even mean? Well, it turns out that there is a handy theorem that gives meaning to e to a complex power. So let's say we have a complex number as our exponent. What does that mean? Well, we have something we call Euler's formula. E to that complex power, we have e to the x. So we kind of split this up as e to the x times e to the iy. But the e to the iy turns into cosine of y plus I times sine of y. So here we're kind of somehow our exponential turned into trig functions. And in fact, this is a very important connection between exponential and trig functions. This is kind of why, if you remember the hyperbolic functions, hyperbolic sine and hyperbolic cosine, these are actually defined in terms of e to the x, but why we give them the name sine and cosine, because they're actually very much related to e to the x in the same way that sine and cosine are if you look in complex numbers. We're not going to prove this theorem. You could actually approach it using the Taylor series for the e to the x sine and cosine, but for the sake of time, we're not going to focus on that here. Just be aware that this does make e to the x work very nicely even for complex numbers, including the fact that the derivative e to the x remains e to the x in complex numbers as well, whatever that means, since probably we haven't really gone over derivatives in complex numbers, but it works. So that's really all we need to know at this point. It just means that when we look at e to the lambda t and we differentiate it, we're going to get lambda times e to the lambda t. That's the main thing. We can pull out those lambdas. And so this differential equation will still actually work when we use complex numbers. So let's go ahead and look at our differential equation, where lambda is complex eigenvalue with eigenvector x corresponding to lambda. Now, none of the problems I'm going to give you are going to have the A here actually be a complex matrix. We're not going to have any of our differential equations written out with complex numbers already in them. So we're going to start with a real situation and then suddenly get complex numbers coming up in that. But because A is going to be a real matrix, that also means that its conjugate, lambda bar, is also an eigenvalue. And it also means that x bar, because the x here is actually going to be a complex vector, x bar is also going to be an eigenvector, but corresponding to lambda bar. Remember, the conjugate just means that we're replacing the imaginary part, the part with the I in it, we're making that negative, but leaving the real part, the part without the I, as whatever it was to begin with. So we have two solutions. Well, I guess we start out, this means that we have two solutions, e to the lambda t times x, and e to the lambda bar t times x bar. Any linear combination of these is going to be a solution as well, including y1 equal to 1/2 times the first one, plus 1/2 times the second one. That's a t. Also, their difference with the 1/2s. So these are two solutions. But the important thing about these is because of the way we set this up, e to the lambda bar t times x bar is actually the complex conjugate of 1/2 e to the lambda t x. So we're adding a complex number to its conjugate, technically a complex function to its conjugate. When you do that, and in fact maybe I'll go ahead and put that off to the side here. When you take a plus bi and you add it to its conjugate a minus bi, what happens? Well, the bi's cancel each other out. We're left with 2 times a. That's why we have the 1/2s in here, because when we add these together, we're going to get just the real part, the a, but then we're going to divide it by 2 to just leave the a. So this is what we call the real part of this number. Well, not number, but the real part of this function. But the point here is, even though we're working with these complex functions, when we combine them in this way, we get a real function. And that's very important. That allows us to actually simplify what we have. So we don't have to be working with complex functions anymore. We can actually get a solution that is just a real function. Same thing kind of here. If we subtract these two things, subtract a complex number and its conjugate, what happens? Now the a's cancel each other out. We have the bi minus a negative bi, so we get 2bi. So if we divide out the 2, and I guess we have to divide out the I as well. Kind of forgot that part. If we divide out by 2i, then that's just going to leave the b. So we get what we call the imaginary part of this. And so most of the time, we're going to go ahead and find a complex eigenvalue. Note that its conjugate is also an eigenvalue. And then we find an eigenvector corresponding to the first one. We don't have to find a new vector for the conjugate. Once we find one complex eigenvalue, we also have, and its eigenvector, we kind of assume that we already know that we have this other pair. And then we'll find these real and imaginary parts and use those because those are real functions instead of these complex functions. That way we can get an actual real solution, something that doesn't involve complex numbers, as our final answer. Because we kind of want to start with a real situation and end up with a real solution rather than complex solutions. Even though we're kind of taking a detour through complex numbers, we get something that actually is a real solution. So that's one thing that people have said in the past, some mathematicians at least, that the shortest way to sometimes to go from a real solution to a real problem to a real solution is through the complex numbers. And that can be taken various ways. But the point here is we're going to look at this other system of differential equations. Now, of course, spoilers here, we are going to have complex eigenvalues, but we're going to see how we can actually use that in this particular situation. So we proceed exactly the same way that we did in the last video. We're going to first turn this into a matrix. We have 3, -2, 2, 3. We're going to look at where we're going to subtract lambda from each of our diagonal elements. When we actually take this determinant, we end up taking 3 minus lambda times itself, and then we subtract -2 times 2, so we add 4. If we expand this thing out, we get lambda squared minus 6 lambda plus 13, and we want that to equal 0. Of course, this is not something that's easily factored. In fact, unless you're willing to think about what are the complex factors to it, then this is actually something that you don't want to even attempt to do. But we can use the quadratic formula. So remember, we have -b, or b in this case is 6, so we have 6 plus or minus the square root of 6 squared minus 4 times 13 times 1. That actually turns into a -16. And then we have to divide by 2. Well, 2 times a, but the a in this case is 1. We can actually go ahead and divide that through. So the 6 over the 2 is going to be a 3. We'll have a plus or minus. This is a 4i. Remember, the negative here we just pull out as an I, and then we take the square root of 16 is 4. But then 4 divided by 2 is just going to leave us with a 2. So our eigenvalues here are 3 plus or minus 2i. So again, they come as a pair of complex conjugates. We have 3 plus 2i, and we have its conjugate 3 minus 2i. We only need to find an eigenvector for the first one, for 3 plus 2i. So we'll go ahead, and we do need to actually go and put this in here. So we take these 3's and we subtract 3 plus 2i from them. Maybe I'll go ahead and write that out, because it's a little bit more complicated than what we had before. Here we have 3 minus, well, the 3's actually cancel out. We'll have a -2i. Same thing here. We have a -2i. And I claim here that the first row and the second row are multiples of each other. In fact, if you were to take this first row and multiply it by I, what happens? Well, obviously the -2i becomes a the -2 becomes a -2i. -2i times I, well, the I times I becomes a -1. So that cancels out the negative we have there and leaves us with a 2. So that's why we actually do have this as an eigenvalue. This is actually something that we can simplify down, something like -2i. Actually, let's even get rid of the negative here. We can cancel out the negative. We have 2i, 2, and this is 0, 0. Just using the same row operations that we used before. We need to find out some vector, some eigenvector here. It's our x, where I'm just going to go ahead and pick 1 for the second component. But we're looking at where 2i times our first number. Actually, I guess I should have just gotten rid of the 2. Make that I and 1. I don't know why I didn't do that. But we have I times our first number plus 1 times our second number equals 0. That's the idea. And if we pick 1 for there, well, what does that leave? That leaves I for that one. Because you can think of it this way as I times I is -1 plus 1 times 1 gives us 0. So that's our eigenvector. If we take our e to the lambda t, so our lambda here is 3 plus 2i times t. So keep in mind, this lambda is multiplied by t. It's not just, we're not just putting that number into e to the x, times this vector. And we're going to expand this thing out. So remember, this thing here is e to the 3t times cosine. So here, keep in mind, I'm distributing the t. So this is really e to the 3t plus 2ti. But using Euler's formula from before, the real part of e of 3t is put on the e. The imaginary part, 2t, is then going to be inside cosine and a sine. And that's still being multiplied to I1. I'm then going to go ahead and put that through. So e to the 3t cosine 2t. But I'm actually multiplying this by I, so this has an I in front of it. Then we'll still have an e to the 3t sine t, but we have the I here times that I there, so actually I times I is negative 1. That's our first component. Our second component, now we're going to go ahead and multiply this whole thing by 1. So really we have e to the 3t cosine of 2t plus I times e to the 3t sine of 2t. Now, why did I distribute the e to the 3t? Well, I'm going to now take the real and imaginary parts of this product, of this whole thing. So the real part, which I guess we were calling that y1 before, is just going to be the ones in this matrix, in this column vector that don't have the i's in them. So this first I times e to the 3t cosine 2t, that's going to go away. We're just going to be left with this part. We end up with the negative e to the 3t sine of 2t. And then here, only the cosine part stays. E to the 3t cosine of 2t. And you might say, well, maybe we should pull out the e to the 3t now. I'm just going to leave it as it is. Then we'll also take y2. This is going to be the imaginary part. I left out my t, didn't I? There should be a t there. Alright, hopefully I can fit this in here. But we're taking only the parts that have an I in that. That means the sine is not going to be in the first part. We're just going to keep the cosine. We're not going to leave the I in there. The I is going to go away, but we're keeping the terms that had an I. So the first component will be e to the 3t cosine of 2t. And our second component is going to be this e to the 3t sine 2t. Okay. Guess I underestimated how much room I needed for this problem. So we'll continue it on another page. But there's not a lot left to do. We're just going to combine these two solutions. We're going to add them together. So here we're going to take y is equal to a constant times y1 plus a constant times y2. That means we have c1 times this thing here. Actually, maybe I'll just go ahead and copy that, so I don't have to rewrite it out again. And then we add c2 times the other one. And then we're going to go ahead and actually distribute this. So here we have c1 times this first part. So negative c1 e to the 3t sine of 2t plus c2 e to the 3t cosine of 2t. And then we have c1 e to the 3t cosine of 2t plus c2 e to the 3t sine of 2t. In fact, well, we could actually pull out the e to the 3t if we wanted to, could say that our first function, y1 of t, is e to the 3t. Actually, even because the negative's there, I'm going to go ahead and put the cosine part first. We have c2 cosine 2t minus c1 sine of 2t. Then our other function, our y2, again, we pull out that e to the 3t. This time, the cosine is actually multiplied by c1. Sine is multiplied by c2, and it's positive. And that's our solution. You can take those functions, you can plug them back into this original equation, take their derivatives, and see that they are combinations of those two functions. So no, we did get an answer that has no complex numbers in it. There's no i's involved in this formula at all. These are real functions. But the fact that we do have sines and cosines instead of just exponentials shows us that there was an influence of complex numbers. We could never get this kind of solution if we only had exponentials in there without using complex numbers. Now, one final note before we end this video, I'll note for bigger systems, we may have a mix of complex and real eigenvalues. We would do the same process as we did in the first video for the real ones, and we do this process from this video for the complex ones, and then we just add them together. So this whole linear combination thing. We have the parts from complex eigenvalues we do this way, and then the other terms we do just the technique from before where we just had the exponential functions. So this is just a part of the more general idea. But this is how we address those complex eigenvalues. We can't ignore them. We have to actually do this separate process for them. And the fact that we did get this kind of solution where we have sines and cosines is in fact really important in a lot of applications. So these can be, this could mean something like, well, these functions, well, maybe they build and build and build as we go through time, which is what the exponentials do. Or maybe if they have a negative exponential, they decay over time. But we might have something where we end up with some oscillation. That's where the sines and cosines come in. And we may not know that originally from our system of differential equations, but we actually see that pop up in our solution, and that's only going to happen if we have those complex numbers in there. So I'm going to leave it off there. I'm not going to get into all the applications of all this stuff. That's left to a differential equations course, and definitely off topic here. But the main thing is that we're working with eigenvalues, and this is a very important application of eigenvalues. So in the next video, we'll actually see it, not necessarily a new topic, but we're going to actually take what we've been working on and go one step further. So we'll see you in the next video.